You see it all the time, right? These polls that tell us what an entire country is thinking. But have you ever stopped to wonder, how on earth can asking just 1,000 people reveal the minds of millions? It feels like magic. Well, in this explainer, we're going to pull back the curtain on the incredible statistics that make it all possible.
I mean, seriously, it sounds impossible, doesn't it? A tiny little fraction of people representing the whole country. It's one of the biggest questions people have about statistics. And honestly, it's a great question, but stick with me because by the end of this, you're going to get it. You'll know exactly how it works.
So let's treat this like a puzzle, all right? The polling puzzle. To solve it, we're going to break it down into smaller, more manageable pieces. We'll start with something way smaller and easier to wrap our heads around.
Yeah, forget about millions of voters for a second. To really understand how this works on a massive scale, we first have to understand it on a tiny one. So we're going to shrink this whole problem down to just five students and their test scores.
Okay, so this is where we need to get a couple of key ideas straight. They're probably two of the most important concepts in all of statistics. First, you've got the population. That's the entire group we're interested in. And then you have a sample. That's just a little slice of that group that we can actually look at.
All right, here it is. Our entire population. It's just 5 students. That's it. And we can see every single one of their scores. Now, if we do the math and average all 5 of those scores, we get the true average, the true mean, which is 80.60. Okay? Burn that number into your brain. 80.60. That's our target.
But now, let's pretend we don't have time to talk to everybody. We're in a rush, so we do exactly what pollsters do. We take a random sample. We just reach in and randomly pick out 3 students from our group of 5. So we take the average of just this one sample, and what do we get? 81.67. Now hey, that's pretty close to our true average of 80/60. But it's not perfect, right? It's a little bit off. And that little difference? That's what statisticians call sampling error. It's not a mistake. It's just the natural, expected variation you get when you look at a slice instead of the whole pie. Okay, but here's the really important question. The sample we just picked, that was just one possibility, right? It was pure luck. What would have happened if we had randomly picked a different 3 students?
Well, because our group is so small, we can actually do something amazing. We can figure out every single possible combination of 3 students we could have picked. And that's what you're looking at here. There are exactly 10 possible samples. Now look at that last column, sample mean. See how every single sample gives us a slightly different answer? Some are a little too low, some are a little too high. This isn't a mistake. This variation is totally normal. It's expected.
Now, I know what you're thinking. This just looks like a random jumble of numbers, but it's not. I promise you, there's a hidden pattern in there. And finding that pattern, well, that's the key to this whole thing. This collection of all 10 of those possible averages, this has a special name. It's called a sampling distribution. And honestly, the best way to think about it is like a map. It's a map of every possible result our little poll could have given us. It's not just a list, it's the entire landscape of what could happen.
And here's where the magic happens. This is the big reveal. If you take all 10 of those different sample averages from our map and you average them, what do you think you get? You get 80.60. Exactly, 80.60. That's the true average of our entire population we started with. This is so important. It means that even though any one sample might be a little off, the process itself isn't biased. On average, the samples point straight to the truth.
Okay, so we've established that samples are going to have some natural error. That's fine. But, and this is a big but, it is absolutely vital to understand that not all errors are the same. Not even close. There's a world of difference between that predictable, random error and just a bad mistake.
Let's break them down. On one side, you've got your good error, sampling error. That's the natural, random wobble we just saw. It's unavoidable, but the cool thing is, we can predict it. We can work with it. But on the other side, you have the bad error, non-sampling error. This is the human stuff. This is when we mess up. And this kind of error is avoidable, it's dangerous, and it can make an entire poll totally worthless.
And these bad mistakes, oh man, they can pop up anywhere. Maybe you didn't pick a truly random sample, or you wrote your questions in a really confusing way. Maybe people just didn't tell you the truth. Or it could be as simple as somebody fat-fingering a number when they were typing in the data. Honestly, a huge part of a pollster's job is just hunting down and stamping out these kinds of non-sampling errors.
All right, so that's how sampling works with 5 students. It's pretty cool. But how in the world do we scale that up? How do we go from 5 kids to, say, 300 million people? For that, we need to bring in the big guns. We need a statistical superpower, and its name is the central limit theorem.
I'm not exaggerating when I say this is one of the most powerful and, frankly, beautiful ideas in all of mathematics. The central limit theorem, or CLT for short, says something amazing. It says that if your sample size is big enough, and big enough is usually just 30 or more, then that sampling distribution, our map of all the possible sample averages, will always form a perfect, predictable bell curve. And here's the craziest part. It doesn't matter what the original population looked like. It could be a total mess, and it would still work.
Let's actually see this in action. It's like magic. So look at step 1. You've got this messy, weirdly shaped population. No rhyme or reason to it. Now, if you take a bunch of small samples from it, like in step 2, the map of their averages is still kind of messy. But then, watch this. Once your sample size gets big enough, like 30 or more people, boom, step 3. The averages magically sort themselves into that perfect, clean, predictable bell curve. This is what makes polling possible on a giant scale.
And the CLT gives us another awesome piece of information. The bigger your sample is, the less guesswork there is. The bell curve of all the possible results gets tighter, it gets taller and skinnier. And what does that mean? It means your one sample is way more likely to be super close to the actual truth.
Let's put some numbers on that. Imagine we're polling employee wages. With a small sample, say 30 people, our wiggle room, our standard deviation, is about 68 cents. Okay. But watch what happens as we ask more people. At 75 people, that error shrinks to 43 cents. At 200 people, it's all the way down to just 26 cents. You see the pattern? This is exactly why pollsters don't just ask 30 people, they ask 1,000 or more. They want to make that bell curve as skinny as possible to get a result that's incredibly precise.
Okay, deep breath. We've got all the pieces of our puzzle now. We get samples, we get sampling distributions, and we've got our superpower, the central limit theorem. So let's put it all together. Let's use what we've learned to look at a real-world polling situation and see what we can figure out.
So here's the scenario. A candidate for mayor is going around saying she's got 53% of the vote locked up. That's her claim for the whole city. We're a little skeptical, so we decide to run our own poll. We're going to ask a random sample of 400 voters and see what they say.
Now, we know our one little poll probably won't land exactly on 53%, right? There's that sampling error. But thanks to our superpower, the CLT, we know that if we did 1,000,000 polls, the results would form a nice bell curve right around the truth. So we can ask a really smart question. If she's right, if the real support is 53%, what are the odds that our poll would come back as low as, say, 49%? The central limit theorem lets us look at that bell curve and calculate that exact probability.
And the math gives us an answer. The probability is just 5.48%. So think about what that means. If she's telling the truth about having 53% support, then there's only a tiny, roughly 1 in 20 chance that a random poll like ours would show a result below 49%. So it's not impossible, but it's pretty darn unlikely. We can now actually put a number on our doubt and make a much more informed decision. So there you have it, the magic behind polling. Turns out it's not really magic at all. It's just math. It's the predictable, reliable power of random sampling, all guided by that incredible central limit theorem. It's what allows a small, carefully chosen group to act like a mirror for the entire population. So, the next time you see a poll in the news, you won't just see a number, you'll know the amazing statistical journey it took to get there.